High schoolers who are especially interested in mathematics and science are encouraged to apply to spend their summer at UC Santa Cruz at the California State Summer School for Mathematics and Science. The Cosmos Summer School gives students who are talented in the sciences the opportunity to explore cutting-edge research and learn what college life is all about. Cosmos is organized by the UC Santa Cruz Educational Partnership Center as part of a larger outreach effort to improve access to college. The 4-week Cosmos program in June and July is for gifted math and science students from 8th grade through seniors. 10 courses are offered at Cosmos, with topics ranging from environmental biology and toxicology to aspects of applied computing. Cosmos is also offered at the UC Davis and Irvine campuses. Cosmos encourages interested students, parents, and teachers to call 831-460-3077 for information, or to visit the Cosmos website at http://epc.ucsc.edu/cosmos/.
Good morning, Cosmos students, Upward Bound students. I hope you all had a very pleasant weekend. We're very fortunate today to have another member of our illustrious Earth Sciences Department, Professor Justin Revenaugh, who received his PhD from MIT and has been on the faculty at UCSC for 11 years. Professor Revenaugh is an expert in the application of seismology and geodynamics to the determination of Earth structures at many scales. So I think we should all welcome now Professor Revenaugh, who's going to talk to us today on the very interesting topic of volcanoes and hot spots. Professor Revenaugh.
Thanks. Thank you. Is this loud enough for everybody to hear me clearly? Okay, great. So I'm going to talk to you today about volcanoes and hot spots, and not volcanoes in general, but the specific type of volcano known as a hot spot. And it's a very important topic. It's related to many things. It's related to the breakup of Earth's continents. It's related to mass extinctions throughout Earth's history. It's related to the diversity of life on Earth. And it's also the creator of some of the great resort islands in the world, like Hawaii, Iceland, the Azores, and many other fun destination places. And I want to give you a sense of how that works today, the importance, and also point out some of the hazards associated with these types of volcanoes. So I'm going to start in with a little map of Earth's plate boundaries. Now, I don't know if you're familiar or not with plate tectonics, but it's a theory in the earth sciences which explains how the Earth's surface has evolved through time. And it's actually fairly simple in outline. The Earth's surface is something like a jigsaw puzzle. The outer portion of it, which is between about 50 to a couple hundred kilometers thick, fairly rigid, is a system of plates. Now the yellow lines up there, which are a little bit faint here, but I think you can probably see, demark the different plate boundaries. And there are some very major plate boundaries. South America sits on a plate, North America sits on a plate, all of this, Alaska, and even part of Japan, or actually all of Japan, may be on that same North American plate. It's hard to tell. Australia down here and India are sitting on a plate. We call these plates because they move coherently, meaning this whole plate here that carries South America is moving. In fact, it's moving slowly to the west with time. Now think about this. If you're moving pieces of a jigsaw puzzle relative to one another, you're going to have a problem. You can slide the whole jigsaw puzzle, and that'll work. But if you're going to move individual pieces in different directions, that's not going to work because they're interlocking. So to move them relative to one another, you either have to create overlaps or create gaps. And that happens in the Earth. And we get both overlaps and gaps, and that's very closely related to how the planet evolves. And I'll click ahead and show you. This is where active volcanoes exposed at the Earth's surface are. The little red dots are volcanoes that have either erupted in human time or at least in the last 10,000 years. And you can see there's quite a few of them. If we could count the dots, I believe there's about 3,000 dots on this map, many of which are overlapping, so you can't see them all. But if you look in detail, almost all of them are very close to a plate boundary. There's a plate boundary along here with a lot of volcanoes. Plate boundaries all along the Western Pacific, volcanoes all around the Western Pacific. You've probably heard the expression, the ring of fire, describing the circumference of the Pacific because it has volcanoes around most of it, and it also has plate boundaries around most of it. We have volcanoes in Oregon, Washington, and going up the Canadian coast and into Alaska, but that's all plate boundary again. What's happening there, that's a place where plates are overlapping. In this particular case, up here, say, in the instance of Western Canada and Alaska, the Pacific plate is moving more or less north and a little bit west relative to the plate that North America sits on. And the Pacific plate is pushed under North America and actually dives down into the interior of the planet to be recycled in the system. You lose that amount of plate. As that process continues, it makes volcanoes, and that's what's responsible for Mount St. Helens, Mount Rainier, Shasta, all the volcanoes that we're familiar with in California. It's even related to Mammoth down in, well, central eastern California. Those volcanoes can be fairly dangerous. They're fairly unpredictable. They create huge ash clouds. And if you're, well, I suppose none of you were alive when Mount St. Helens erupted. Shows how old I am now. But if you've ever seen any of the video from it, it was a pretty spectacular eruption and covered most of eastern Washington and Idaho with ash. Let me find some other places with volcanism. Not shown as dots on this because the volcanoes are underwater are a series of volcanoes that run along the middle of the Atlantic Ocean, on the base of the ocean. And I'm kind of tracing it out here. This is all volcanic. There's eruptions along there pretty much every day. And that's the case where the plates are spreading apart from one another, creating an opening. And to fill that opening, you need to create new plate, and the process of creating new plate is volcanism. Volcanoes bring material from the deep earth up to the surface. It cools and becomes new plate. So that allows those pieces to keep moving apart without there being a gap. You keep filling in the gap. Okay, that accounts for almost all the world's volcanoes. That's not the type I'm going to spend my time talking about. Before I get to the type I'm going to talk about, I'm going to show you where Earth's seismicity is, earthquakes. If you live in California, you're fairly familiar with earthquakes. Well, here's where they are. And this is about 10 years worth of seismicity. These are all earthquakes that if you were nearby it, you would feel it, and feel it quite strongly, in fact. So these are all magnitude 5 and above. And you can see that they also populate the plate boundaries of the Earth, too, and very closely related. There's some places like here in the Himalayas and the Tibetan Plateau where we have fairly diffuse seismicity without a plate boundary, but there used to be a plate boundary there. Yeah, there's a question. And so the question was, how are the plate boundaries calculated? So assuming by that, how do we know where they are, is the big question. Well, the way we know is sometimes it's obvious. In the case of the San Andreas, if you've ever flown, say, down to LA from San Jose, you can look down and see the San Andreas Fault. It's a very obvious feature on the surface of the Earth, and that's a plate boundary. But typically, we know it from volcanism and seismicity. Those are the calling cards of plate boundaries. And so when we look at this map, the earthquakes themselves are sort of giving us an idea where the plate boundaries are. Most of them you can't go to and see. Okay, so all the earthquakes are happening on the plate boundaries, but we have the occasional oddball one. And I don't know if you can see that dot, but it's right there at the index finger of the pointer. Earthquakes in Hawaii. And they're actually fairly deep earthquakes. They happen about 50 kilometers down, some of them. which is sort of odd because we're nowhere near a plate boundary in Hawaii. We're right out in the middle of the Pacific Plate, one of the largest, and about as far from a plate boundary as you can get, and yet we have seismicity. All right, so here are hotspots, the thing I'm going to spend my time talking about. They're the big red dots here. The size of the red dots means something, which I'll come back to in a moment. There are 50-some dots on this chart, and you can see that some are happening near plate boundaries. This is Iceland up here. It's happening near this boundary between the North American plate and the Eurasian plate. And we have some others that occupy plate boundaries here. The plate boundaries are black. Apologize for the change. But we have a lot of these, in the case of these in Africa, sitting in the middle of the continent, and a big cluster sitting in the middle of the Pacific Plate. These are sort of the exceptions to the rule of how volcanoes on the Earth work. And they're actually very important for the entire system of the Earth and how it functions as a planet. The scale here, how big the dot is indicating how much lava is coming up out of these different volcanoes. And the biggest one here is Hawaii. And to give you a sense of what is coming out of Hawaii, which is actually fairly amazing, Hawaii puts out 200 million cubic meters of lava a year. Right? 200 million cubic meters, that's a number, you know it's large, it has absolutely no meaning. So to try and make that more meaningful to you, that would fill Lake Tahoe in 750 years. Right? Now you might be thinking, well, that's not so much, but Lake Tahoe is really a very deep lake, so that's a lot of lava to come out. But maybe more meaningful to you is it would cover 40,000 football fields 1 meter thick each year. Right? Now 40,000 football fields is that's a lot of area to cover. A meter thick is a lot of material. All right, Iceland up here is putting out about half that much. These Tahitian islands and other islands in the South Pacific are putting out amounts close to what Hawaii is putting out. So we're covering the planet, if we were to spread this lava out every year, a few inches thick. There's a lot of material coming out. All right, so what I want to do with the rest of the talk is give you an idea of the process of that, both the surface manifestation, what these volcanoes are doing at the surface, and where they're coming from. Okay. I don't know why I have that in, other than it has names of some of these hot spots on it. So some of the big ones I'm going to be talking about. Hawaii, we all know where that is. I'm going to be talking about Iceland up here, and the Columbia River, and more in particular, Yellowstone. These are all major hot spots on the planet. Okay, let's go to Hawaii first. So who here has been to Hawaii? Raise your hand if you have. Right. Who here has been to the big island of Hawaii? Smaller number. The big island of Hawaii is the one that's most active today. The other islands are largely dead volcanoes. Hawaii is still a very active volcano. I want to show you some slides of volcanism, and then I'm going to show you a video of it as well. Okay. All right, so this is an active vent on the big island of Hawaii. It's spewing out lava here. Lava is just magma that's come to the surface of the earth. It's really synonyms other than we call it magma when it's in the subsurface, lava at the surface. This is a particular type of lava known as basaltic lava. When it cools, it makes that black rock. It's very hot. For this stuff to flow, it has to be at least 1,150 degrees Celsius. To put that into Fahrenheit, that's 2,100 degrees Fahrenheit. It's really hot. Catches trees on fire long before it even gets to it. If you get close to it, your hair starts to burn. You don't even have to touch it to be burned badly by it. This lava fountain here is being thrown up to about 100 meters height. Now, why is this stuff bubbling out like that? Well, a good analogy to why the lava bubbles out like that is when you open up a can of soda or pour a glass of soda. If you've ever looked at it, you see these little bubbles jumping out of it. That's the carbon dioxide that's been put into the soda to give it the fizz coming out of solution. And as it comes out, it throws these little specks of soda up in the air. Well, the lava has gas in it, and the gas is coming out of the solution as well. And as it does that, it throws lava up into the air. It's a much larger scale process, so it can throw it up many hundreds of meters. There's another huge lava fountain. And you can see the material, as it goes up, is red hot. It's cooling off in the air and coming down as black ash. That ash would still be hot. If you touch it, you'd burn yourself. But it's cooled off enough that it's become rock. That'll give you a sense of scale. If you look, there's a helicopter. And I think there's a depth perception thing here. That helicopter is not very close to the lava fountain. At least I hope it's not. So this is another lava fountain. You get a lava river here. That stuff can run fairly fast, especially when it's hot. To give you an idea, it can move up to about 50 kilometers an hour. Right? So that's fairly fast. I mean, that's Highway 17 most of the time. Traffic jams on it. Here's a fissure. Most of the volcanism on the Big Island of Hawaii right now, it's not coming out of one central vent. It's coming out of a long, continuous fissure that's about 50 kilometers long, runs from the center of the island out to the eastern coast. And it's just bubbles up like this on occasion. Most of these slides are actually from a big event that happened in the 70s. And since then, the volcanism's been active, but not spectacular like it was then. So here's a long lava river flowing along at about 20 miles an hour. Yeah, this will give you a sense of when this slide was taken by those two guys' sense of style. This lava flowing along and refilling an old crater, which was an active vent at some point in the past, not active now. Another lava lake forming down here. You can see how as the lava cools, it forms a little crust on top. And it's almost like plate tectonics for the planet. This little lava lake is covered up with little continuous jigsaw puzzle pieces, which are rock floating on the surface. Another big old lava lake. This one's really hard to get a sense of scale, but that's about 3 miles across. It's about 3 kilometers or 3 miles across if you go from here all the way to the far side. So this is the back rim of the crater, and we can't see the whole thing in the slide. Very often the lava is running underground. As lava is exposed to air, it cools, and so often these lava rivers will become lava tubes. So lava on the surface will solidify, lava at depth, not exposed to air, is cooling more slowly, continues to flow, and you get these, what essentially is like plumbing, runs along in a tube. Here's a place where the roof of the tube collapsed and you can see back down to it, and these are called sky holes. And you can tell it's pretty hot. You're dead. The question is, what happens if you fall through one of those? It won't take long, so you won't be in pain for very long, but that will kill you. Remember, it's 2,100 degrees Fahrenheit at minimum. It could be hotter than that. It could be up to 3,000 degrees Fahrenheit. Your lifetime in that is not even a second. There's another lava tube that's had a roof collapse. There's looking down into one where you can see the lava still flowing. That guy is playing with fire, literally. So here's another lava fountain. We don't see the lava, we see the ash that's blowing up. This large blocky stuff here, which looks like it might be ground cover, is lava. It's cooled off, but it's still moving. It's flowing very slowly and coming through this forest and killing the trees. This is a lava tree. It actually was a tree. The lava flowed through and turned the tree more or less to charcoal, but the structure of the tree remained intact and is embedded in frozen lava here, so it's covered up in rock. Another lava tree here. There's a big flow. The little Things here which look like a bad slide aren't a bad slide, those are trees. So this is lava moving through a forest and destroying it. This is the surface of the material after it's cooled down a little bit. Kind of looks like a rug that's been pushed along. That's because, again, the surface stuff cools more quickly than what's at depth. What's at depth continues to flow. What's at surface gets more solid, less easily flowing. And so it sort of bunches up just like if you tried to push a rug. Okay, that's the slides. I'm going to switch to video now.
Hawaiian volcanoes are renowned for their approachability. The recent prolonged activity at Kilauea has provided many unique opportunities for detailed observations by scientists from the Hawaiian Volcano Observatory.
Watch this guy try and get a sample, give you an idea how hot it is.
The characteristics of Hawaiian volcanism that make it so readily accessible are consequences of special properties of Hawaiian magmas. Generally, they are quite fluid and lack the large amounts of dissolved gas present in continental magmas, like those feeding Mount St. Helens. While explosive events are generally absent in Hawaii, lava may still be ejected from the vent with considerable force. Towering fountains result from the pressure behind a constricted flow and the expansion of gases within the rising magma. Great quantities of molten material can be thrown into the air during episodes of high fountaining. The lava expands and becomes frothy upon leaving the vent, forming products such as ash, pumice, cinder, and Pele's hair, which can drift downwind for great distances. Magma can also well to the surface much more quietly. Over a period of extended gentle activity, lava may pool above the vent, eventually forming an active lava lake such as Kupaianaha. In this case, lava can erupt quietly at the vent because much of the gas is released from the magma as it flows beneath Pu'u'o'o. Lava lakes develop as levees build up around a vent.
Okay, that's enough of that. Oh, okay. All right, I'll give you 20 more seconds worth.
Flowing freely over the ground and instead forcing it to pool. This levee is being built by spattering around the edge of the lava lake. Partially hardened, the lava pond crust still appears amazingly flexible. At times, the level of the lake is high enough for lava to spill out. Over a period of months, repeated overflows from the lake form a broad, growing mound called a lava shield.
Okay. I heard everybody laughing at the active vent, Pu'u'o'o. It's its real name. We're going to talk a little bit more about Hawaii now. This is a map of the central and northwestern Pacific Ocean's bathymetry. The colors here give you a sense of water depth. Here's the big island of Hawaii emerging from the water, so it's green color here. The lighter the blue, as we see up here in the Bering Sea, is shallow water. The darker blues are deeper water. And you can see that island of Hawaii and the other islands in the chain form a nice little linear arc here. That continues on quite a ways, with a bend in it and going all the way up here to the tip of the Aleutian Isles. That's all related to the same source of magma and lava. Right now, Hawaii is sitting over that source. At different times in the past, these different areas along the chain were sitting over that source. It's been there for quite a while, pumping out a lot of material. To get an idea of what's going on here, boy, you're going to have a hard time reading that. So I'll read it to you. So the Big Island of Hawaii sitting down here, its average age is about 400,000 years. So it's a fairly young feature geologically speaking. To give you an idea, the Earth is over 4.5 billion years old, so something that's not even a million years old, geologically speaking, is fairly young. So we go up the chain, the last island to break the surface is Midway Island. Sits right here, it's 27.2 million years old. And if we go out to this bend in the chain, this is an island called Daikakuji. It's not an island, it doesn't break the surface. We call it a sea mount, meaning it's a mountain under the ocean. And it's about 42 million years old. So what's happened here is sitting underneath Hawaii right now is a source of magma. That magma hasn't moved. What's been moving is the Pacific plate above it. So the analogy here is imagine putting a candle on a table and running a sheet of paper over it, and burning a hole through the sheet of paper by moving the sheet, not moving the candle. So there's that fixed source of magma sitting right here now, but 42 million years ago, it was still where it is now, but the plate was in a different position, so that Daikakuji was sitting over it. Well, that distance, let's work it from Hawaii up to Midway. That's about 2,400 kilometers, 2,400 kilometers from here to Midway Island. And the difference in age is a little less than 27 million years. If you do the math there, if you divide 2,400 kilometers by about 27 million years, you get 9 centimeters per year. That's how fast, on average, the Pacific plate has been moving, about 9 centimeters a year. That's about how fast your hair grows. Right? So it's pretty slow movement, but if you give it millions of years to move, that'll move quite a distance. So that Pacific plate's just been moving along, moving to the north and to the west, now for over 80 million years, because that's how old these island, or seamounts are up here, and creating this long chain of islands. Here's a bigger picture of the bathymetry in the Pacific. We can see the Hawaiian chain marching along, and then that bend and going more northerly. But we can see some other chains in here as well, island chains swinging along. Now, the way we recognize these things as being hot spots is because they make these chains. The source of the magma doesn't move, the plate does, so you get these linear rows of islands and seamounts. I want you to look at this and try and guess where the active centers of volcanism are. We have one at Hawaii at the tip of this chain. So I'm going to give you like 20 seconds to look up there and see how many other hotspot chains you think there are. And I'll give you a sense for it. There's more than one and less than 10. All right, let's click ahead. And in the next diagram, we'll put the red dots where the active centers are. So we have Hawaii. We have Tahitian Islands here, multiple sets. This one that sits right off of a major plate boundary between the Pacific and Australia. You can see its little chain kicking up. These ones have chains behind them as well. And there's one little chain down here that we don't know what to do with yet. You can see marching along there. It's being recycled. Pacific plate's diving underneath the Australian plate here. But we don't know what made that one. So there's still work being done on this. Where that active center is, we don't know. You can also see up here, there's Yellowstone, which we're going to come back to. So this names the different hotspots, the Hawaiian one, Tuamotu, Pitcairn Island, McDonald, and the Austral group. And you can see that Hawaii gets up to about 80 million years old before it hits the tip of the Aleutians out there. All right, why do we get island chains? Well, let's think about the process here. We have this fixed source of magma down here, and above it, a plate that's moving. So with time, that magma is rising to the surface. Why does it rise to the surface? It's hot. That makes it less dense than the material around it. It's buoyant, and it rises up. Burns a hole through the plate, which allows it to come out and create volcanic islands. Once it's burned that hole, it will continue to come out through that spot until that hole, which is moving off here to your left, gets too far away from the source. Right here, the source is right under the volcano it's forming. This one got too far away from the source, so it's no longer active. This one's even older and less active. This one has been built up enough that it's above the waterline, so that's like the islands of Hawaii. Why are the older ones not above the waterline anymore? Well, a couple reasons. The big reason is those islands are sitting there and being worked on by the waves. Waves crash in, does a lot of work on the island, wears it down and erodes it down. You also get massive landslides on these islands. Hawaii's had landslides that are just amazing in scale. You might not care about that, but there is a reason to care. If one of those were to happen today on the eastern shore of the big island of Hawaii, as large as some of the ones we see in the past, it would create a tsunami, a tidal wave, that would reach campus. So that's a reason to care. Will it happen? Yes, it's going to happen. There's nothing we can do to stop it. It's happened in the past. It will happen again. So as the plate moves, it creates this island chain. They get older and older, more and more eroded. This is showing the little coral reefs on them. Builds up around the island when the water is shallow enough, when the volcanic edifice is built up enough. Coral reef can keep up with the changing water depth for a while, and eventually it drowns it. So this is going from an active volcanic island to an atoll to a seamount, something that's totally under the waterline. All right, let's look for some other hotspot tracks. We're going to go to the southeast Atlantic and Africa here. I'll give you an idea. The African plate is moving sort of in this direction, up and to your right. So we can see some fairly obvious bathymetric features here, which look like it might be a hotspot chain of islands. But see if you can guess how many are there. I'll give you 10 seconds to look at that. Here we go. There's a bunch. The dots are small here because they don't put out a lot of lava. The big one's sitting right there. So African plates moved away from it and left this long scar. This is a pretty young one, which is why it doesn't really have much of a track. And here we have this chain, a little hard to see. And then here's one that's on land, or just barely off land at this point, and it's left this chain, which again is a little hard to see, but it's there. Here's the northern Atlantic. We're going to do the same exercise. There's hot spots out here. The question is, where are they right now and how many? So there's a pretty obvious track. That looks like a track. Maybe this. Here's where we know them to be by the fact that they're active. So there's a chain right there. We had this long chain. And we don't really know what to do with it. Well, it turns out, or it's not obvious what to do with it, it turns out that that's actually the source of it, right there. And you might be thinking, how the heck does that work? Because here's a plate boundary. This is the North American plate. This is the northern part of, well, what is that? That's the Cocos plate. This boundary between those two has been slowly moving to the west, so that this spot right here used to be on this plate while this plate was moving to the west. So it's left this long, weird chain because of how the plates are moving with respect to it. Right, those are pretty hard to see, I admit that. Let's go back to the Pacific Ocean where it's a little simpler. So here's the active hotspots. The thing I want to explain to you is, why is there this bend? Hawaii goes along as the most obvious chain of islands, and then there's this sharp 60-degree change in direction as it heads up north. Well, let me show you why that's happened. All right. So this is going to be a little MPEG movie. It's going to show you what's been happening in the Pacific Ocean for the last 85 million years. It's a little jumpy because we don't know the full history of this. So sometimes the clock is moving, but the plates aren't moving. That's just because we don't know what's going on at that time. But this is the part to watch right down here. This is the modern day Pacific plate. This one up here is one called Kula, which is an Aleutian native islander's name for gone. And it got that name because it's gone now. This plate's no longer around. This one is called Farallon after the Farallon Islands. This is the Pacific. What I want you to watch is the direction it's moving through time. Because remember, the Hawaiian hotspot is sitting out here, creating these islands, and the plate's moving over it. So just watch the direction it goes. See that little change in direction right at 42 million years? Let me back it up. Go. So it's kind of moving that direction right now. Moving north, 42 million years, and we get a little kink off to a more westerly direction. That's what caused that bend in the Hawaiian Islands. It's sort of important for California as well, because up into about 30 million years ago, there was the the Farallon plate subducting underneath California, and that's what gave us the Sierras. The Sierras are no longer being formed. That process turned off about 30 million years ago when we went from a boundary where a plate was being subducted under California, was going diving down underneath of us, causing a lot of volcanism, to a case where we had the San Andreas Fault moving through California. So we've had a continuous history of bad hazards, volcanoes that were creating a lot of ash and lava, to the San Andreas Fault. Okay. So, I've kind of given you a sense of what happens for these hot spots and the volcanism, especially when it occurs out in the oceans. I'm going to switch now and give you a sense of where they come from. So why is there these fixed sources of magma somewhere in the mantle? So I want to tell you about where these hot spots come from, where the source of magma is. So here's a slice of the Earth. Here's the core down here. Most of it is liquid iron. They don't actually show you, but there's a solid portion of iron in the middle. The rest of this that you can see here is called the mantle. It's made out of rock. Pretty much any rock that you find at the surface is similar in gross sense to what the mantle is made out of. And this whole material is not static in the mantle. Yeah, there's a question? So the question is, what would happen if Dr. Evil did get the atomic bomb down there? I don't actually know. My guess would be basically nothing. All right? There'd be a blast down there. Seismographs around the world would detect it, and life would go on completely unchanged. I think if you're going to set off a bomb, that's probably the safest place in the world to do it. Made for a good movie, though. So this material here in the Earth's mantle is not static. It's actually moving. And it moves very slowly. It goes along at maybe 10 centimeters a year, but it's moving. Why is it moving? The planet's hot. As you go down deeper and deeper into the Earth, it gets hotter and hotter. Hot things want to cool off. Space is cold. Planet's hot. The planet is cooling off. The way it gets its heat out is twofold. One, it just conducts through. So this is the idea: if you turn on a gas burner and you put the pan on it, the pan gets hot. Eventually boils the water in the pan. That's heat diffusing through the pan into the water. That's a process which happens in the Earth, but it's not very efficient at cooling the Earth. The way the Earth does most of its cooling is to take hot material that's at depth in the Earth and move it up to the surface where it can be in communication with the air or the oceans and cool off more rapidly. We call that process convection, and that's how the Earth is cooling itself. Hot material at depth comes to the surface, cools. When it cools, it's no longer buoyant, it becomes denser and sinks back down. It's essentially a lava lamp. If you've ever seen a lava lamp, you have this big blob of brightly colored stuff that sits at the bottom of the lamp for a little while and then rises up to the top slowly, sits there for a little while and then falls back down. Why is it doing that? Well, a lava lamp is basically a big thing of vegetable oil with wax in it. The wax is brightly colored. That's what we think is the lava. And it's sitting in the vegetable oil. And when they're at the same temperature, or more or less same temperature, the wax has about the same density or a little greater density than the vegetable oil, so it'll sink. When the wax gets down at the bottom of the lamp where the bulb is, it gets heated up because the bulb is hot. As it heats up, it becomes less dense, it's buoyant, and it slowly ascends up to the surface, or to the top of the lamp. And when it gets up to the top of the lamp, it cools off, becomes more dense, sinks back down. The Earth's materials and the mantle are doing exactly the same thing. They're getting heated up by the hot core, rising to the surface, cooling down, and falling back down to the bottom. It makes a little nice continuous cycle. Well, how does that material come up? It comes up as not a big, broad welling of fluid up. It comes up in plumes. And that's what's being shown here. Here's one that's a little younger. It looks basically like a big balloon with a string on it. This is all hot material rising from the core towards the surface of the Earth. And when it hits the surface, you're going to have a lot of volcanism, but that tail of it is going to continue to have material fluxing through it, and that's what's happening in Hawaii right now. You have material that's coming from about 3,000 kilometers depth in the Earth, hot, rising all the way to the surface and erupting in Hawaii and those other hotspot islands. I have another little slide of that, giving you a sense of how these things evolve. So here's hot material down at the base. It starts making this little bubble. We call that a diapir. That rises fairly quickly through the mantle up to the surface, spreads out, starts erupting as lava, creating large islands, or if it's on hitting on a continent, it's making volcanic edifices, mountains. And you can see that that big blob spreads out. It takes a while for it to all get through and be erupted, but after a long time, all you're left with is just the tail and material coming up through that. So the big question here is, if Hawaii, which is putting out a lot of lava, is just material coming through this tail, what happens when this big head, this big ball of lava, which starts the process, gets to the surface? And that's a pretty good question, and that's where I'm going to turn to now. So this is back to a picture of some of the major hotspots with their names. What I want to draw your attention to are these gray patches here, here, up here. You can see them. There's a few of them on there. These are called flood basalts. It's basaltic rock, same material that makes up the island of Hawaii. We call them a flood because it's basically come up in large volume and spread out just the way floodwaters do. And you can see, like in the case of the piranha here in South America, that's covering a lot of ground. South America is a large continent. That's covering a large portion of it, and it's not a thin veneer of basalt. That's basalt that in places is kilometers thick. Up here in Siberia, we have a thing called the Siberian Traps, another deep, broad deposit of basalt. The Deccan Traps in India, the Karoo in South Africa. They didn't even bother to show, well, I guess it's right there as a little dot, that we have one in North America called the Columbia River basalt. That's actually, even though it's the smallest one on this map, is the one I'm going to focus on because it's closest to home for us. So here's a map of northwest United States, Washington, Oregon, Idaho. This area here, which is kind of a slightly different blue than what's around it, is all basalt. And it's called the Columbia River Flood Basalt because the Columbia River flows through it. It's the Columbia River Basin. That material is about 15 million years old and was formed rather quickly. And in places, the basalt here is several kilometers thick. So if you were in the northwest part of the United States 15 million years ago, you would have been watching volcanoes spewing out lava that looked very much like what you saw in the Hawaiian video, covering an area which is basically the size of a good-sized state. Right? Everything living there would either not be there anymore or would have been killed, because you can't live through that. Nothing would live through that. So that would have been a very bad time in the Pacific Northwest. Give you an idea of the amount of material we're talking about there. The Columbia River basalt, if we spread it out over the entire continental U.S. uniformly, it would be 1 foot deep. Right? So it could have covered the entire U.S. 1 foot deep. That would have been very bad because it would have killed everything in the continental U.S. Let's see. So here's the topography of the Pacific Northwest. What I was showing you was that 15 million year old deposit sitting right up here. That was formed when one of those plumes, convection in the mantle, cooling off the mantle, reached the surface. So that big head of magma came up and was erupted in a very large deposit. The tail is still there. The little string on the balloon is still there with magma moving through it. I said before where it is now, it's Yellowstone. Can anybody see the track that it's followed? Just remember, just like the Pacific Islands, there's going to be a trail. Yeah. See this? That's, yep. Southeast here? Okay. Well, this is the Columbia River showing up. So the trail is actually going off to the southeast, you're right, comes around and then heads back to the northeast. It's the Snake River plain there, but that's the hotspot track. And if we click ahead, there's the little dot. It's a small dot because Yellowstone's not putting out a lot of material right now. It did 15 million years ago, but that's its trail, up like this arcuate path. Why is it following an arcuate path like that? Well, the North American plate has moved that path. This dot, in a fixed sense, hasn't moved. The plate's moved over it, and it's taken a sort of odd trajectory. So there's the Columbia River basalt. I said it was 15 million years old. That was an average. It started 17 million years ago, and the last small activity ended about 6 million years ago. And you can see this line of volcanoes that goes up to the present Yellowstone area, differing in age, 16, 14, 12, 11, 10, 6, 4. They're getting younger and younger as you move towards the active center of volcanism today. All right. I'm going to show you slides both of Yellowstone, but first I'm going to show you slides of a volcanic event that happened in Iceland in the 70s on a volcano called Jaime. It's a sort of famous scenario. Here's a little fishing town down here of Jaime. This is a little coastal community. Not a lot of people live there. They rely on fish for basically their entire income. This volcano started erupting and threatening town, but also threatening their port. Now, usually when a volcano erupts and starts threatening, the thing you do is you leave and you hope it doesn't ruin everything. These people were a little bit more resolved than that. They pumped seawater out to the active lava flows to try and cool them off and keep it from destroying their town, and it worked. Now, usually that's a futile effort. You can say that maybe they got lucky and it was just chance, but they actually put this one off from destroying their town, but not completely. There was a lot of damage, which I'm going to show you. So here's what we call cinder cone. This is magma coming out, being erupted. This is ash that's forming. It's rock. We call it ash. It's not ash like what you get in a fireplace. It's rock, but in very small pieces, little flecks, like talcum powder almost. And that's falling down. As it rains down, it makes this little cone almost like an anthill. But some of it gets blown further. Here is another lava fountain. You can see it cooling off into ash, and the wind kind of shearing the ash over right now. There's a couple Jaime residents. The lava fountain and the ash in the background. This was a flagpole. Right? That's how far up the ash came. There's the town of Jaime. That's a house. That's the ash. They're walking home right now. There's another house and a street light. This is just all ash that came out of the volcano. It wasn't a lava flow. It didn't destroy the house, but you're going to have to dig it out. So they won the war. They saved their port, but they lost a lot of homes to the eruption. We're going to go to Columbia River now. That's about as good as it gets here. This is the Columbia River. This is the Columbia River Gorge. You can see this large terrace face here going all the way down to the level of the plains here. That's all basalt going all the way down to the ground there. That's the Columbia River flood basalt. The river's cut its way through it and eroded out this channel. But that'll give you some sense when you look over here at how thick a blanket that is near Seattle. This is cross-sections. We're looking into the face of one of those river terraces. All of this, and this is about a ½ kilometer high, is basalt. You can see different flows in the past. Here's some topography that had formed from erosion and river channels cutting it, and then another flow superimposed on top of it. Didn't all come out at once, but it came out over a fairly short period of time and would have been pretty catastrophic, or was fairly catastrophic. This is a more young flow in the Snake River Plain. This is the basalt. You can see it's covering a huge expanse here, an edge of where the flow got to. So it's slow-moving basalt ponding out and basically destroying everything it flowed over. This is young enough that there's still no vegetation on it. And these are a couple of the hot springs in Yellowstone National Park. This is where the volcanic center is now. You might think hot springs are no big deal as far as threats to people, and they're really not unless you do something stupid like put your head down it. But it's giving you an indication that that hot spot is not dead. There's still hot material being brought to the surface. Here's a nice, another vent, steam vent. One of the thermal ponds, water that's, you know, it's a little too hot to be a hot tub. This would definitely scald you. There's a picture of Steamboat Geyser while it's going. You can see nice steam cloud going up. We're going to skip that. I was kind of hinting at the fact that maybe Yellowstone isn't as innocent as it might seem with its beautiful topography and geysers. This will give you an indication of just how bad it could be. Mount St. Helens erupted a little over 20 years ago. The major eruption cut down aviation in the Pacific Northwest for quite a while because of the ash cloud. People lost their lives taken by it, a lot of inconvenience for transportation, even ground transportation, because the ash was meters thick and it's much, much denser, heavier than snow, so it's very difficult to plow it. This was the area that got covered by the ash, and out here at the end of this, that was very thin layer of ash, thickest up here. And it's just showing you the wind patterns that took this ash as it was created and blew it downstream. The other colors here, centered around the Yellowstone caldera, the present spot of the hot spot that made the Columbia River basalt, shows ash flows from the not too distant past. The big one here that I'm circling right now, the Huckleberry Ridge ash, was erupted 2 million years ago out of Yellowstone and covered basically the mountain and Pacific time zones. And then more recently, 600,000 years ago, we had the Lava Creek ash, which covered Texas, all the way up into Oregon, all of California, Nevada. And that wasn't a thin patina of ash. We're talking in some places up to, well, around Yellowstone, meters to tens of meters of ash. And down in Texas, it's down there that you're getting to a couple inches of ash. It's a lot of ash. It's a huge amount of ash. If that happened today, we would be cut off from the Eastern time zone. No planes would be flying through that for probably 6 months. No trucks would be coming through. It's fine for us. We have all the fresh produce we'd ever want, but the East Coast wouldn't get any. So there's hazards still associated with Yellowstone. There's hazards associated with all of these hotspots. There's some good things associated with them as well. One, they make great resort islands. If you've ever been to a place like Hawaii, you know it's physically very beautiful. And if it wasn't for hotspots, we wouldn't have that. It's also, in an odd way, related to the diversity of life in both positive fashion and negative fashion. I'm going to show you the negative fashion first. So the little diagrams, I apologize for how small it is, but I stole it off the web. It's showing the last 300 million years of geologic time. Here's the present. This is 300 million years ago. Don't worry about these little letters down here. They mean something to geologists. They don't need to mean anything to you. The y-axis here is the percentage of extinction of genera. Right, so this is fairly high up in the taxonomic divisions. And we're talking about up here, 70% of all the Earth's genera being extinct, being killed at once. Right? So that's 70% of the Earth's faunal and flora diversity being wiped out. And that happened at about 250 million years ago. It's one of the largest extinctions. This is the one that took the dinosaurs out down here, the KT boundary, as you've probably heard about it, or heard it referred to as. That got up only to about 40%. So that was actually minor in comparison to this one 250 million years ago. Well, 250 million years ago, the significant thing that was happening on the Earth was that flood basalt I pointed out in Siberia was being erupted. Being erupted, putting out a lot of toxic gases, putting out a lot of ash that got up in the atmosphere and changed the Earth's climate for a long time. And as far as we can tell, if correlation implies some sort of causality, result in destruction of 70% of the genera on the Earth. The Deccan, or the thing called CAMP, it's the Central America magmatic province. This is an eruption that happened both on the east coast of the United States and the west coast of Africa and South America. You might ask how it happened in all those places at once. Those three continents were linked together at that time. They were all shoved together. That one killed off about 40% of all the genera. And then the KT, which we now associate with a large asteroid impact, killed off about the same. So these two magmatic provinces, when they were formed, flood basalts were formed, it killed off a lot of the life on Earth. So that's the negative. The positive is that sometimes these things create new ecological niches. So when that, let me go back to it for a second. When this province was erupted, North America, South America, and Africa were fit together like puzzle pieces. That started a process that opened up the Atlantic Ocean, spread those three continents apart. When you spread those continents apart, you get a lot more shallow water rimming continents. When you put continents together, you reduce the amount of shoreline. When that opened up, we got a lot more marine species, and it actually resulted in a diversification of life. But that came at the expense of killing off a lot of what was there at the time. So there's both diversification and extinction associated with these. Okay, so to kind of summarize, hotspots are a way the Earth cools itself off. They're a natural process of the planet's evolution. They make great resort islands. They're ever-present hazard, not that one will pop up in your backyard tomorrow and kill you, but the ones that are present on Earth today right now have some geologic hazards associated with them. And throughout Earth's evolution, they've both caused massive extinctions and resulted in the diversification of life. I'd like to thank you for being a great audience.